So here we go with related rates once again. Now we're talking about related rates and throwing in our knowledge about derivatives with trigonometry. So we have our 10-meter long ladder leaning up against the wall on a building site, and it starts to slip down the wall at a rate of 0.05 meters per second. Now the difference in this question is it's not how fast is the base moving away from the wall, but it's how fast is the angle between the ladder and the ground changing at a particular instance. So we're going to start by drawing a picture for this. Here's our 10-meter ladder at some distance away from the wall, some distance up the wall, and now we care about this angle theta. And we know that dy dt is negative 0.05 because it's moving down the wall. So what's the relationship between the things that we know? Well, we know that opposite hypotenuse, we know that sine theta is y over 10. And you might be saying, well, why not cosine, why not tangent? Because this x, we don't know anything about the x. We know nothing about that side. So I'm going to try and write a relationship between something that I know about, dy dt, and the thing that I'm looking for, d theta dt. So derivative, let's go. We've got cosine theta d theta dt equals 1/10 times dy dt. So there is the relationship between my rates, between how theta is changing and how y is changing. Now we need to look at the specific situation that we're in. So this is 10, and we want the instance that the vertical height is 8. And if we look at, and we could say that sine theta is equal to 8 over 10, which reduces to 4/5. And I could use the Pythagorean identity to find the cosine of theta down here, which I need, or I can come back to my right triangle that we build with this ladder, and we know that this missing side, x, is 6, so we can just write cosine theta is 6 over 10, or 3/5. And now we can put in our information. Cosine theta is 3/5. D theta dt is what we're looking for, equals 1/10 times dy dt, which is negative 0.05. And we solve this for d theta dt, and we get that theta is negative, d theta dt is negative 1 over 120 radians per second. And in trigonometry, with calculus, we do deal in radians, not in degrees. And we should expect that this is negative because this angle will get smaller as the ladder falls down the wall. Example 2, we have two ships now. We have the Zadar and the Rab. At a given moment, Zadar is 40 kilometers south and 50 kilometers east of Rab. So here is our Rab. Zadar would be over here, where this is 50 and this is 40 kilometers. And we know that this x distance is changing, dx dt. This x distance, the Rab is sailing to the east, so dx dt is getting smaller at a rate of 15, and the Zadar is sailing north, so this 40 distance is going to get smaller also. So we'll say dy dt is equal to negative 12. So those are the rates that were given in here. How fast are the two ships approaching each other after 2 hours? Okay, so now we have to draw a slightly new picture. So Rab, Zadar, this x distance is going to be 50 minus 15 times 2. which is 30. So after 2 hours, Rab is now 30 kilometers west of Zadar, and our y after 2 hours is going to be 40 minus 12 times 2, which is 16. So Zadar is still 16 kilometers south of Rab. And what this is asking for is how fast are the two ships approaching each other. We want to know, if we call this distance, I'll call it P, just for fun. We want to know what is dP dt. So, relationship here, we know that P squared equals x squared plus y squared. Pythagorean theorem. Let's take the derivative. We get 2p dp dt equals 2x dx dt plus 2y dy dt. And notice these all have 2's, so those 2's can actually divide out. We divide both sides by 2. So what is P at this instant in time that we care about right here? Well, P is going to be the square root of 30 squared plus 16 squared. I lie, hopefully you caught this as 20, not 30. So we have square root of 20 squared plus 16 squared, and you could put that in the calculator if you wanted to, which you will need to at some point, times dp dt equals x, which at this instant in time is 20, times dx dt, which is negative 15, plus y, which is at this instant in time 16, times negative 12 is dy dt, and we can solve to get dp dt is equal to negative 19.2 kilometers per hour. All right, so now it says, how fast is the bearing of the Zadar from Rab changing? That means we need to know about this angle. That would be the bearing from the Rab to the Zadar. Bearing would actually be, if this is north, the bearing would be that whole distance, but this 90 degrees stays constant. So we need to know d theta dt in this picture now. And the nice thing is we have our derivative that we found already. We have our distances, but we need a relationship between theta and the stuff that we know. Personally, I know that p is not a nice number. P is an irrational number. So what I'm going to set this equation up as is tangent of theta equals y over x. Y over x, that's the relationship between things that we know and the thing that we're looking for, and now we take the derivative. We get secant squared theta d theta dt equals, now be careful, the right hand side, quotient rule it up. Low d high minus high d low over low squared. And we know x, we know dy dt, we know y, we know dx dt, we know x here. And secant squared, well, that's something we don't know. So we have to do a little bit of work to find that, and we're going to use our triangle here, and we're going to use a Pythagorean identity. We know that secant squared theta is equal to 1 plus tangent squared theta. And the tangent of theta happens to be, at this instant in time, opposite over adjacent, 16 over 20, which reduces to 4/5. At this instant in time, 2 hours after the beginning, the tangent of theta is 4/5. So secant squared theta is 1 plus 4/5 squared also known as 41 over 25. So now I have all the missing pieces, all the parts that we need for this, and substituting our values in, we get d theta dt is equal to 0 radians per hour. So as these boats are traveling, this angle that we have to turn to see the other boat is not changing as we go. That's what that means contextually. All right, one last example. It's a multi-part problem. We have a reef, a coral reef, 120 meters from a straight shoreline that's marked by a beacon. So shoreline I'll do in green, and out here on the reef we have this beacon, and it's 120 meters out, perpendicular. And it's shining a light, and this light is spinning around in a circle, and somewhere over here, there's this point where the light beam hits the shoreline, and that point is going to move. And it's some distance away from, straight out from the shore. So, here's our picture. It rotates 6 times per minute. Okay, so what is that? That's how the angle down here is changing. That's a relationship for how d theta dt is. But d theta dt is not just 6, because what we need to do is we need to turn this into a radians per something. This is 6 rotations per minute. Let's change this to radians per second. So it's 6 rotations per minute. If I want to turn this into radians, 1 rotation is 2 pi radians, and it's per minute, which is 60 seconds. And what we end up with is that this is pi over 5 radians per second. Anytime we have number of rotations, we need to turn it into radians per second. Multiply by 2 pi, divide by 60. Or we really could leave it as per minute if we wanted to. So how fast is the beam moving along the shoreline at the moment when the light and the beam are at right angles, or the shoreline and the beam? So in other words, when x equals 0, we want dx dt. And when x equals 0, well, it happens that theta also equals 0, something to know. So what's the relationship between x, the distance along the shore where the beam is hitting, 120, the distance from shore the beacon is, and this angle that is changing as the beam scoots out along the shore? Well, it's a tangent relationship. Tangent theta equals x over 120. Let's take the derivative. Secant squared theta d theta dt equals 1 over 120 dx dt. There's our derivative. And we know that theta is 0, so secant squared of 0, d theta dt is pi over 5 equals 1 over 120 dx dt. Solving this, we get dx dt equal to secant squared 0. We know that cosine of 0, that's a familiar one to us. Cosine 0 is 1. So secant of 0 also has to be 1 because they're reciprocals. So secant squared is 1. So we have pi over 5 equals 1 over 120 dx dt. And simplifying, solving this for dx dt, we get 24 pi meters per second. You can approximate that if you want to. I'm just going to leave it that way. It doesn't tell me I have to. I'm going to leave it in exact terms. All right, next example. How fast are they when we have 50 for x? So tan theta is 50 over 120, or 5 over 12. We're still dealing with the same triangle, the same relationship, so we still get to use this derivative. But what we need now is we need to know what secant squared is for this instance in time. So now we have 50, 120, here's theta. Secant theta, well, secant squared theta is 1 plus tangent squared. And we know that tangent is 5 over 12, so secant squared theta is equal to 169 over 144. And now we can make our substitutions into this derivative, and we can solve that derivative for dx dt. We have 169 over 144 times pi over 5, that's our d theta dt, equals 1 over 120 dx dt, and we get dx dt is equal to 169 over 6 pi meters per second. What's happening to the velocity of the light when the ray is parallel to the shoreline? Okay, so this is going to take some thinking. It's not just immediately evident, I don't think. But so if the beam is approaching parallel to the shoreline, that means that theta is approaching pi over 2. And if theta is approaching pi over 2, cosine theta is approaching 0. As we get closer to pi over 2, the cosine graph gets closer to 0. Therefore, secant of theta is approaching infinity. It's growing larger without bound. If you look at the graph of secant theta, there's an asymptote at pi over 2. And what that means is that secant squared theta is also approaching infinity. It's getting infinitely large. And so dx dt, if we use this formula right here to find dx dt, if this is getting infinitely large, if we multiply that by pi over 5 and then multiply by 120, that means that dx dt is approaching infinity. That beam is getting faster and faster and faster and faster, crazy fast as we get way out over here. So there we go, 3 related rates examples, some involving trig, some sort of involving trig, but not really, and it's really nothing new. So have a great time.